So welcome for the next session on Module 1, and here today we are going to discuss the subsidiary laws that incorporates the three modes of heat transfer. The first one that we are going to discuss is our Fourier's law, and in this particular law, this particular law governs conduction. So Fourier law is predominantly used in case of conduction. So whenever a Viva question is asked, like which particular subsidiary law governs conduction, your answer should be Fourier law. Fourier's law, sorry, Fourier's law. So in case of Fourier's law, let us take a solid, all right, and let's say we choose a random direction n. Of course, we can also have Cartesian coordinate system, but let us choose a very random direction n. Then, according to Fourier's law, it says that the heat flux, that is, let's say this is the amount of heat divided by per unit of surface area, heat flux is proportional to temperature gradient in that particular direction. Okay. So what exactly is temperature gradient, and we will see a little later on. This is just the statement part. So here you see you have your heat flux, which is heat is usually, rate of heat transfer, it is watts divided by meter square. And here your temperature gradient, so temperature in this case is the delta T represents change in temperature, so this is your degree Celsius. You can also write it in Kelvin, not an issue, because when it comes to change in temperature, numerically both are equal, either degree Celsius or your Kelvin. And the direction, you can any direction, if you measure the length, then that is your meter, and degree Celsius per meter. So if by any chance, like we remove this particular, sorry, so if we remove this particular proportionality, we will write it as k into dou t dou n, where t is a function of n. Like depending upon which direction you choose, temperature will vary differently. All right. So suppose it is you choose the Cartesian coordinate system, the temperature variation in x direction will be different than in compared to y direction, and then compared to z direction. All right. Now what is this particular term k? It is called as a very important parameter. It is called as your thermal conductivity. All right. And what will be the unit of this thermal conductivity? See, this was watt per meter square, and this is degree Celsius per meter square. So if we just do a little bit of calculation, we will come to know that thermal conductivity is watt per meter per degree Celsius. Okay, you can also write it as watt per meter per Kelvin, because change in temperature is same in case of degree Celsius or in case of Kelvin. All right. So this is what we have with respect to Fourier's law. Now, the noteworthy point is that there is a negative sign that I have used. And what do you understand by temperature gradient? Let us see on that particular part. Okay. So let's say we have a block. All right. And let's say it's a furnace wall. All right. Let's say it's a wall. And this wall has a certain area. All right. And this is the area that we are considering. And heat is given to that particular area from let's say flame. We are giving the heat, and the temperature on this surface, let's say it is T1, and the temperature on the other surface, which is exposed to environment, is, let's say, at temperature T2. All right. So since the furnace flame is on this side, definitely T1 will be greater than T2. And let's say the length of this particular furnace wall is L. All right. And the area that we are talking about, this furnace wall area, is, let's say, A. Okay. Now we are giving certain amount of heat. Let's call this as Q dot. So heat flux on this particular wall will be Q dot by A, and is equals to temperature gradient. See, temperature is decreasing from T1 to T2, correct? So over the length L, the temperature is decreasing. Sometimes people take it as L, sometimes people take it as the thickness of the wall, which is a small t also. Whichever suits you, you can take that, not an issue. So this is equals to K into, let's say in this case, we are choosing this particular random direction. It may be X, Y, Z, I don't care. Let's say we take it as a direction N is equals to, and temperature variation only happens in this particular direction, so we are taking it as the absolute derivative rather than partial derivative. Okay, now in this case, you see this temperature gradient is actually final temperature minus initial temperature divided by the change in, I mean, like whatever distance we are considering, so that is your thickness. Okay, the final temperature is T2, initial temperature is T1 divided by L. All right, now in this case, you see, since T1 is greater than T2, so this particular gradient will come as less than 0. Now, since we want to have a positive heat flux, I mean, like, which is just a convention, nothing hard and fast. So since we want to have a positive value for Q by A, and since the gradient will be negative always, so we are putting a minus sign here. This is the justification for it. Also, thermal conductivity, as you can see, is directly proportional to this whole particular scenario. And as a result, higher the thermal conductivity, faster will be the heat transfer from this end to this end of the wall. All right, so that is why metals will have higher thermal conductivity. If you see the general chart of thermal conductivity in case of your data handbook, you will see that metals have higher thermal conductivity compared to non-metals. Also, metals first it will come metals, then after that there will be drop in thermal conductivity with respect to alloys. Then you will find non-metals. Then you will find your liquids, and lastly you will find your gases. This is the usual order of decreasing thermal conductivity. So pure metal definitely will have higher thermal conductivity, and this is your Fourier's law. Okay, and the next one that we need to discuss is your convection, or the subsidiary law which governs convection, that is your Newton's law of cooling. All right, now when Newton conducted this particular experiment, he essentially took into consideration the cooling of a body, but it does not mean that the same law cannot be uh, used whenever there is a heating of the body. All right, so in this case, suppose we have a surface which is maintained at a constant temperature of, let's say, TW or TS, whatever you want to call it. It's better if I just call it TS. Let's call it its TS. It's the surface temperature. All right. And let's say a fluid, since it's convection, so there has to be a fluid which is either heating or cooling a body. So there is a fluid, and let's say the fluid temperature is T infinity. This is the usual notation for ambient temperature or fluid temperature, so you can take it, not an issue. Rather than to avoid ambiguity, I will just, as of now, I will mention it as TF, which is your fluid temperature. All right. Now there are two scenarios which can happen with respect to this. If Ts is greater than Tf, then this will be cooling of the body. All right. And if Tf is greater than Ts, then this will be heating of the fluid. All right. So in case of Newton's law of cooling, what we need to know is that the law says that the heat flux, see again, uh, depending upon whether the surface is a higher temperature than the fluid. Let us say I will go with the first case, and in this case Ts is greater than Tf, then some amount of heat will be going out from the surface to the fluid, and there will be an area of the plate as well. All right, so the amount of heat flux means heat that is leaving a particular surface or coming to a particular surface per unit area, that is a heat flux, much like your flux in case of in case of magnetic field, or maybe in case of light also. So how much magnetic lines of forces are passing through a particular area is called as a magnetic flux, whereas how much amount of light is passing through a particular area is called the flux with respect to light. Now in this case, Newton's law of cooling, he said that heat flux is directly proportional to the temperature difference. Now temperature difference, I will write it as Ts, and I don't know which particular case will come. You see, I have chosen the first case, but um, both the cases are possible, so I will write it in this way, which shows that whichever is greater will be written first, subtracting the other term from it. All right, so that means this will always be positive. You will write it in such a way that this should always be positive, unlike your temperature gradient in case of your conduction, where it will be negative. This will always be positive. Now if I remove the proportionality sign and put a constant, all right, and represent the temperature difference as delta T, then this is called as coefficient of heat transfer. All right, and again we can very easily find out uh, the unit for particular this particular parameter, and it will be just, and it will be, let's, I will write it this one again, q dot by a is equals to h into delta T. So here this is watt per meter square, a unit of this one, and unit of this one is degree Celsius or Kelvin, whatever you want to write. So unit for H will be watt per meter square per degree Celsius, or if you give the temperature difference in Kelvin, then this will be watt per meter square per Kelvin. Both are correct. All right. Now heat transfer coefficient is such a complex parameter. It's a very complex parameter, and it depends on a lot of other physical parameters with respect to a fluid motion, because fluid motion is involved in case of convection. So you will be dealing with the density of the fluid, then viscosity of the fluid, all right, then velocity of flow, all right, thermal conductivity of the fluid, all right, and so on. There are so many parameters. Also, these are like fluid properties. It can also depends upon the orientation or surface roughness. Okay, so these are not related to any fluid. These are much more related to uh, the solid from which the heat transfer is taking place. What I'm trying to say is that, see, let's say I have a plate and I keep it in two position. All right, this position, and we are blowing the wind in this direction, and similarly, I mean, like, and in the second case we are blowing the wind in the same direction, but we have kept the plate in this position. So definitely there will be different amount of heat transfer from both the cases, and that usually happens. See, area of the plate has not changed. Okay, also the surface temperature and the ambient temperature has not changed. So what changed is just the orientation of the plate has changed, and because of that, uh, your heat transfer rate will be different in both the cases. So definitely this is a very complex parameter which depends on so many other things, and hence there is no one specific value. So every time you have to, like, if a convection scenario is given to you, you have to actually calculate the heat transfer coefficient. Now in your data handbook there are certain standard configuration that has been tabulated, and people have over the years have conducted experiment multiple times, and then they have given those correlations. So if your experimental setup matches one that is mentioned in your data handbook, you can use the formula given in the data handbook to calculate the H value, and then you can use Newton's law of cooling. So it's not so simple. Until and unless in a numerical problem they give you the H value and they ask you that it will be constant for whatever scenario. To be honest, when Newton's initially proposed the law, he also assumed that the H will be constant. Later on, over the years, people found out that it's such a complex parameter and that it does not remain constant, and with a slight change in any one of these parameters, uh, H value will vary drastically. All right, and when it comes to convection, also there is your natural convection and there is your forced convection. So two very uh, different approach has to be there while solving those kind of problems. Okay, so this is all about your Newton's law of cooling. Let us go into the third subsidiary law, which is your Stephen-Boltzmann law. Now, when it comes to radiation, all right, when it comes to radiation, there are actually four subsidiary laws. The first one is your Stephen-Boltzmann. Stephen-Boltzmann law. Next one is your Planck's law. Third one is your Wein's displacement law. Or we can also call it as Wein's law. And the fourth one is your Kirchhoff's law. Okay. Now, in this case, we will just discuss Stephen Boltzmann, and when we go into the radiation chapter, we will discuss the other three types of law. All right. So these there are four subsidiary laws, and depending upon what kind of situation we are dealing with, we will use one of those subsidiary laws in case of radiation. Now, in radiation, you see, it's very simple. Stephen Boltzmann law says that if a body is at an absolute temperature, remember this is absolute temperature, so temperature has to be measured in Kelvin, unlike in case of conduction and convection where you can also use degree Celsius, because in those cases we were dealing with only your temperature change, but in this case we are dealing with the absolute temperature of the body. So so Stephen Boltzmann law says that if a surface is or a body is at an absolute temperature T, then heat flux from the body is proportional to the fourth power of the absolute temperature. So if you just remove the proportionality and introduce the constant, which is called as a Stephen Boltzmann constant, now remember your Stephen Boltzmann constant, there is an experiment in your lab where you need to determine the Stephen Boltzmann constant, and its value is fixed 5.67 into 10 raised to minus 8. And what will be the unit? So again we can very easily find, so this is watt, this is meter square, and this is Kelvin to the power 4. So this unit will be watt per meter square Kelvin to the power 4. So this is the unit for your Stephen Boltzmann constant. So this is the first subsidiary law, and remember there are a lot of other things that goes into radiation. That means there are cases where uh, you deal with a blank body and then you deal with a real surface, but then real surface have to approximate it as a gray surface. So all these things we will discuss in detail when we go into the radiation chapter. All right. Now let us move on to one-dimensional steady-state heat conduction law. We have so far we have gone through some of the subsidiary laws, but now let us see what happens when we use those subsidiary laws for one-dimensional analysis. That means we are considering heat transfer is happening in one direction only, and other direction heat transfer is too neglected. All right. All right. So let us start with one-dimensional steady-state heat transfer. Now, what do you mean by steady state? That means, see, steady state it's a very tricky question. So let us say I have a bar and I place a few thermocouples on the bar to measure the temperature. Then I start heating it. All right. And let's say this is temperature T1, T2, T3, T4, T5. Five thermocouples have been placed and we are measuring the temperature at these five locations. Now you understand is that whenever this heating starts, heat will flow in this particular direction, and the temperature of these junctions where we have placed the thermocouple will tend to increase. So this thermocouple will register a change in temperature with respect to time. All right, so temperature of T1 will initially and will also be higher since it's closer to the burner, will be higher compared to T5. There is a gradual decrease in temperature, but yes, this particular point its temperature is increasing with respect to time. There will come a moment, All right, after heating is going on and on for a considerable amount of time, there will come a moment when the heat sent into the bar because of this burner will be equal to the heat going out from the bar, because see, this is at a higher temperature than the ambient air. All right, so definitely it's receiving heat, but it's also rejecting heat. As the heating goes on and on and on, there will come a point where the heat received is equals to heat rejected. So energy in will be equals to energy out. That particular scenario is called as your steady state. Okay, now you see here, steady state, theoretically it means temperature doesn't change with respect to time. All right, so people usually get confused, but sir, temperature of T1 is higher than T5. Yes, temperature of T1 is higher than T5 with respect to location. Yes, it will change, but for one particular location, the temperature of T1 after steady state has been reached, it will not change. So for one particular location, it will not change when steady state is reached, but from location to location, it may change. So don't get confused with respect to the concept of your steady state heat transfer. Okay. All right. So let us just go through an expression with respect to your steady state heat transfer. Okay. So let's say we have a furnace wall. All right. And the length of the wall, or the thickness of the wall, and this is the width of the wall. So this is the width. All right. So width is much greater than the thickness. All right. So you will see a significant amount of temperature change in this direction, but in this direction you will not see so much of a significant change in temperature. So what we are going to do when we say one dimensional, it means that we are neglecting this particular part or this particular direction, and we are considering only this particular direction where the thickness is very, very small, and we will see a significant temperature drop in that particular direction. Okay. Let's say here the temperature is T1 and here the temperature is sorry, T2, and let's say the thermal conductivity of the material is K, and let's say some amount of heat is going from, so this is the heat flux going from this direction, and since steady state is there, so whatever heat flux is going in, same amount of heat flux is going out, as we have already discussed it, what can be considered as a steady state. All right, so here let's say we take only the direction, let's say this is an x direction, so we are considering only heat transfer in the x direction. Now we can say that temperature is a function of direction x. That means it varies only in the direction x. We are not bothered about direction y or z. Okay, so we can write it as q by a is equals to minus k into dt dx. All right. Now in this case, since I want to find out, I mean, like, I don't want a differential equation, I want a exact solution of this equation. So what we need to do, we need to integrate, as simple as that. Okay, so we make it as q by a into dx. All right, this will be minus k into dt. Let us integrate. So x changes from 0 to t, and here the temperature initially was T1, then it becomes T2, final temperature is T2. Since flux is constant, so flux will come out of the integration sign, and this will be only integration of dx from 0 to t. And here, since thermal conductivity, we are also assuming it to be constant. All right, it will be from T1 to T2, and it will be with respect to dt. This will be q by a into t, and here it will be minus k into T2 minus T1. So as T2 minus T1 is less, so we can reverse it and we can write it as Q dot A is equals to minus, or we can remove this minus sign. Right? We can remove this minus sign and we can write K into T1 minus T2 divided by T. So this is your expression with respect to one-dimensional steady-state heat transfer in case of a slab. All right. Now we will also see one-dimensional steady-state heat transfer in case of a cylinder. All right. So one-dimensional steady-state conduction in case of a long cylinder. All right. Now let us draw a tube. This is the cross section of a tube. All right, and this is the part where we have the material. All right. Now in this case, let's say there are two scenarios that will come. So this is at a radius Ri, inner radius Ri, and this is at an outer radius or not. Okay. Now previously, in case of a slab, you see, heat is going in this direction. Let's say some amount of some kind of okay, sorry. There's some kind of a fluid is moving inside, which is at a temperature Ti, and there is ambient air, okay, which is at a temperature, let's say T out, To, I will write it. Okay. Now definitely heat will move in this particular direction. It will move in this particular direction. But in this case, see, Q dot is fine in steady state, but the area will not be constant because it's a tube and the curved surface area keeps on increasing. As curved surface area increases. All right. Now, if you want to do the calculation again, so again we will have here Q dot by A. Fourier standard Fourier law we are going to use minus K into dt dr. This time the heat is going in radial direction, so we are taking as dt dr, and we are going to integrate this side. Let's make some adjustments. So first we will write Q dot A into dr. All right, and this will be integrated from Ri to R naught, and this side it will be minus K, and integration from Ti to T naught, and this will be dt. Now if you take any random radius, any random location in the ring at a radius r, so the curved surface area will be 2 pi rl. Length of the pipe is same from the inner radius to outer radius, that is not changing, so that will only be r dr, and here we will get minus K into dt Ti to T naught. Now if you do the integration, since Q dot is same, it will come out 2 pi L will also come out. Only thing that will remain is dr by r from Ri to R naught, and here we will get K into Ti minus, I'm directly writing it, Ti minus T. Now from here this will be Q by, sorry, this will be Q dot by 2 pi L, and 1 by R dx by x is ln r, and this will be Ri to R naught, and this will be K into Ti minus T naught. So if you just simplify this will be q naught into ln r naught by ri divided by 2 pi kl is equals to ti minus t naught. Okay, or q dot is equals to 2 pi kl ti minus t naught divided by ln r naught by ri. So this is your expression, sorry. So this is your expression for heat transfer in case of your cylinder, long cylinder. Right. Next case that we are going to take is that of a sphere. So we're taking into consideration one-day conduction in case of a sphere. The same thing goes if I take a cross section of a sphere. All right, this is at a radius ri, this is at a radius r naught, and this is the material which having a thermal conductivity K. And also there is an ambient there is ambient air which is moving over this, and inside there is a fluid which is at a temperature of Ti. So in this case also you can see the area of the sphere is changing from the inner hollow part to the outer hollow part, so area is not constant here. So similarly again we are, if we use Fourier's law, it will be q dot by a minus k into dt by dr. Same thing here also, heat is going in the radial direction. All right, so if we integrate it, I mean, like, let's adjust it. Q dot by a into dr is equals to minus k into dt, and if we integrate this will be from ri to r naught. If we integrate this will be from ti to t naught, and q is constant, so it will be coming out. And if we take a random location at a radius r, then this area of a sphere, also surface area of a sphere, is 4 pi r square dr. This will be k into ti minus t naught. Sorry, here I have written q. All right, so now q dot by 4 pi will come out, and all will be left out is the r square, and this will be ri by r naught. So will be k into ti minus t naught. And what is the integration of 1 by r square? It will be minus minus 1 by r. This is essentially r to the power minus 2, so this will be r to the power minus 2 plus 1 divided by minus 2 plus 1. So this will be minus 1 by r. This will be ri2 r0 ti minus t0. So from here I will just continue here. This will be q dot by 4 pi, and here it will be 1 by ri plus 1 by r0. Sorry, ri minus 1 by r0. This will be q dot by 4 pi, and this will be r0 minus ri, and this will be ri into r0. So final expression is q dot 4 pi, sorry, this side it is k into ti minus t0 ri minus r0 minus ri into k into ti minus t0 divided by r0 minus ri. So this is your final expression with respect to the sphere. So let us stop this session here, and we will again join shortly.